Okay, so let me just. Okay, so this is lecture 9. Let's go to our lecture material. Previously, we have thought about neural network, and now this is the second time and the last time because we will not spend much of our time to this topic, and we will come back to original computational microelectronics 1. So in this semester it was just a teaser of our future investigation. Yes, so we will just make a very simple neural network for detecting handwritten digits. So please make your reference on this address. This is numpy, so this is basically for basically the Python library. I don't think that this is the only way to do this job, but maybe it will be quite helpful to most of us to refer this website. So please have a look at this one, and if you have done it already, then maybe you have those files like mnist train.csv file and test.csv file. So you will have tons of data, and from these two files you can generate images and labels. So homework number 8 was devoted to detecting or showing, visualizing the images taken from these two files. So please make the entire data set. They can be, for example, a matrix whose rows are 60k and whose columns are 784. This is corresponding to the training data, and this is for image. And here you have another vector, although the number of rows is the same, 60k. However, it just say a single number. This is just 0, 1, 2 up to 9. So you can have quite a simple vector for your training set. Quite similarly, even for your test set, you can also identify this is for your image and this is for your label. So please prepare these four variables in your code, and this figure just shows that the distribution of each digit in our training set. There are 60k. So if everything is ideal, if every digit is uniformly distributed, then for each digit you will have 6,000 items. And please have a look at this count. So this is just fluctuating around 6,000. This is corresponding to 6,000. Some of them are more frequently occurring and some of them is less frequently occurring, but it is not that much. So this is about 9%, and this is corresponding to 11%. So more or less digits are evenly distributed. So first of all, you have to prepare those variables, and let's try to build a small neural network. So small means that, well, nowadays we have quite a deep neural network, but this is not that deep. So it has only one single hidden layer here. So of course we must have input layer and output layer, and input layer just takes the values from our images. So it is, for example, taking the size of vector size of 784. It is because we have assumed that the image itself is given by 28 by 28 pixels, and the output should be also 10 numbers. So the probability for or strength of a certain digits. For example, let's say that if this is minus 0.1, minus 0.2, plus 0.5, also other numbers smaller than 0.5, then if we have this vector, then we will interpret this vector as this one. Okay, this 0.5, the maximum one, is corresponding to the number 2. So the input we have currently is detected as number 2, or categorized as, classified as number 2. So the maximum one will show the highest probability of that number. Okay, so this is given. Also, this is given for classification job, but here we can introduce many internal layers. However, in this case we will have just a single hidden layer. So simply speaking, our neural network is not deep. This is quite shallow. However, I think that this is just okay to give you what is neural network and how can we implement it from our own effort. So please, let's play with this single hidden layer case. So of course, size of a hidden layer can differ depending on your own decision, but I'm just following the tutorial given in this reference site. So I introduce relatively small one, like 100 neurons inside in this hidden layer. So simply speaking, if you provide certain vector whose size is 784, then it is mapped into another vector whose size is just 100. After that, now it is once again mapped into a vector whose size is just 10. So here you can see this and this and this, and finally this vector is regarded as the strength of that digit. So we will just pick up the entry with highest strength, and that will be the category of our current input image. Okay, so let me explain a little bit more about this one. An image is loaded in the input layer, and this is normalized from 0 to 1. So previously you have the numbers like 0 from 255. So please divide it by 255. So normalize it to 0 to 1 range, and now you have a certain vector. So yes, the range of that vector is understood, so in a row-wise way. So here we have 28, 28, and we have 28 copies of those rows. This is the appearance order of our pixels. Yes, once we have this 784 vector, then that is mapped into this 100 vector. So how can we do that? it can be done by matrix vector multiplication. Here, for example, now we have 784 by 1 vector. Then we can multiply a matrix whose size is given by 100 by 784. Then this internal dimension should be matched. After that, if we perform this multiplication, then we will have once again 100 by 1 vector. So that will be used as the numbers in hidden layer. So then how can we do that? Simply speaking, have your input image. This is your original input image, of course normalized within 0 to 1 range. After that, you can just introduce a certain matrix. It has many entries inside it. So the number of entries is about 78k. So you must determine what are they. Then depending on the entries inside this matrix, of course the result of your hidden layer will change. But right now, just to try a random numbers. So random numbers within certain ranges. So following our tutorial, so each entry is in a range from minus 0.1 to 0.1. So I will, can you see clearly? Okay, so I will use a different color here. So minus 0.1 to 0.1. So you will have such kind of number. And of course, in order to make a reasonable result, actually we have to adjust all of those numbers. However, right now, just start certain value, meaningless values. So yes, then after that, matrix vector multiplication means this operation. Now you have your image and multiplied by certain weighting matrix, although it is not have any meaning right now, but anyway you will get hidden layer data. Okay, then that will be a vector of 100 by 1. After that, this is important, this is taking a non-linear function. So rectified LU is activated. So this is nothing but, if your input argument is positive, then it just copy your input argument. So this is input and output. So your input is just copied for your positive input variable. And if you have negative input variable, then this is rectified and nothing happens. Output becomes just 0. This is okay. So this is the ReLU activation function. So simply means that it introduces non-linearity into your overall system. Why we have to have a non-linearity? If everything is just linear, then yes, we don't have a very complex behavior over our system, and there exists a well-known method to generate some good fitting for those entries. However, it do not give us benefit for fitting everything. So nonlinear function, introducing a certain nonlinear function for activation, that is quite important. That should be introduced. And maybe you know that this LELU is not the only one we can have for this activation function. Although LELU just looks like this, for example, we can use alternative ones like this. For example, such kind of, or even passing 0, or many kinds of different nonlinear functions can be introduced to activate our matrix vector multiplication result. Okay, so however, this is widely used, and in this tutorial also LELU activation was used. After that, finally, dropout. Dropout means that now you have 100 entries of this actions. The actions means that first take the matrix vector multiplication. After that, taking the nonlinear function. So now you have something corresponding to your output. However, randomly select in this case half of them and just eliminate it. Eliminate means that although it was 0.5, so without any reason it becomes just 0.0. Means that we are now doing some pruning. Some sum of neurons inside your 100 hidden layer is just randomly selected and deactivated. So it is known that this is good to prevent some phenomena called as overfitting. So this is the practice we follow. I mean that yes, this is not for our inference phase, but for the training phase. So I mean that once you have really working code, predefined code, then you don't have to do this dropout. That can be skipped. Actually, that should be skipped in your final evaluation. So in this example or in your homework problem, you don't have to do this job. Okay. So now anyhow you get this result of layer 1. Now you have layer 1 result, and after that from layer 1 to layer 2, the output layer is quite simple. You can just multiply another matrix whose size is much smaller than before, 10 by 100. Then it maps 100 entries into just 10 entries, and that's it. That will be the layer contents of output layer, and among them the biggest one, so in a positive sense, is taken as the final result. Of course, up to now I have explained it in this way. I mean that, for example, so let me just write down. Okay. Sometimes our pencil is stuck. Up to now, what we have done is like this. Let's say that the components of our image, or the first layer, is given as a vector called as L0. So this is the contents stored in this part. Then we have multiplied, for example, a matrix called as W1. So that was done here. After that, what we have done is take certain activation function, in this case LELU function. So after that, multiply certain dropout matrix. Some of them is just taken, and that is just So of course this dropout function can be regarded as a diagonal square matrix. So 100 by 1 vector is just mapped into 101 vector, and some of them is randomly selected and become nullified, and some of them is just doubled. And this is our situation up to now, and we will call it as the contents of layer 1. I mean that here we have a short note. No bias term in this example means that in general we can add additional term like so b1 vector, another 100 by 1 vector to this case. This introduces certain biasing for our output variable, but in this example we intentionally neglect this one to make it easier than with the bias term. Well, anyway, so simply speaking, the general procedure is quite simple. Once you have image, then just take matrix vector multiplication, and if that is positive, then keep it, and if that is negative, just make it 0, and after that take the dropout. And yes, if we repeat this job twice, then we will get certain small vector, and this vector is interpreted as the probability, relative probability of having that number in your image. Okay, so now let's first try with random weights. So in our notation, for example, we have to have W1 matrix and W2 matrix, so weight 1, weight 2, and each size would be, for example, mapping, so mapping the original size into the size of a hidden layer, and this second weight just to map the hidden layer into the output layer. We have two different matrices, and their values initially just randomly selected within a range of minus 0.1 to positive 0.1. Okay, so are you with me? This is corresponding to our W1, and this is corresponding to W2. Okay, after that, please try to test your random neural network. Although it is called as a neural network inside it, but its performance would be quite awful, we can expect, because there is just random numbers, no training has been performed. So what we can expect is, for example, although input image is number 2, but this neural network says that okay, it is number 6, and although this is 3 to us, the humans, but it is just recognized as number 8. Of course, this neural network is not trained at all, and it has no idea about what is digit or something like that. For example, in my 10K training set, so I tested it, and the accuracy was just 11 point, about 11 point. So if this is really purely random, what will happen? So maybe you will have the percentage, accuracy percentage of about 10%, because although you randomly select one, but that will be, there will be about 10% probability to select the correct one. So as expected, it performs quite often. Okay, so today we will not talk about details about the training phase. So I will just come back after I have finished. I announced the today's homework. Then I will try to explain a little bit more about the training phase. But for why, just to skip the training phase, I will give you the pre-trained neural network. You can find them in our GitHub repository. So why don't you just visit our GitHub repository together? Okay. So when you have a look at our lecture repository, so I have prepared this CS2 CSV files. So when you click it, then you can find those numbers. Those numbers are having the size of something. So please think about the size of our W1 and W2. It should be, for example, actually not this way. In a matrix form, it should be 100 by 784. However, in actual implementation, I just transposed it. So that's the reason why, although it should have 100 by 784, but it has now the size of, here you can see that 784 rows and columns. There are 100 columns. Please treat this weights 1 as just a transposed form of our matrix W1. Quite similarly, you can also find this one. Now you have 100 rows and only 10 columns. Now performing this matrix multiplication, you can map your hidden layer onto the output layer. So simply speaking, now you have already pre-trained network. So what you have to do is just to download those two files and load those two files, and by using these matrices, please try to test the performance of your neural network. Okay, so these two graphs just shows my training history. So the one you have right now in our repository, GitHub repository, is corresponding to this one, but I think that any of these two is good enough. So I just prepared these two ones because sometimes the result of our training really depends on many parameters. For example, in this left side, we have used a relatively small set. So although we have 60k items in our training set in Taiwan, I just took the very first 1000 items. So data is quite small, and this is the result. And on the other hand, in this case, I have used a full set of our MNIST data set. Also, test set is expanded from 1k to 10k. And if everything is so ideal, then training set and test set should give us quite a similar result. Means that, so let me just explain a little bit more. Training set means that the one really used to train our neural network. We say that, okay, this is number 1, and this is number 2, and this is number 4, and this is number 7. So these are actually used in the training session. So these are corresponding to training set. Test set means that our neural network never seen this number, for example. And what is it? This is our question to our trained neural network. Then maybe it will think whether this is number 7 or number 2, and it will give us a certain number. So the unseen pattern is included in the test set, and training set is actually used in the training. Means that since training sets are used in this case, actually it is easy to get good result for training set. But since test set is not inside our training set, so it is never seen before, so the result of our test set represent the real result of our fitting. Okay, for example, let's think about this case. Some students are trained, or young kids are trained to memorize certain product, integer product of two numbers up to 19 by 19. So let's say that kids are trained to memorize or solve these problems. Okay, he or she can remember and do it quite well. However, if we ask 2 times, for example, if we say 21 by 23, if they really master the multiplication of 2 different integer numbers, although this is not in a training range like numbers below 20 and number below 20, but they should be able to get a correct result out of this one. But how about your opinion? Maybe it is not. And the way we do currently with neural network is, well, we cannot cover all kinds of these numbers because simply these numbers are too many. So what we do is randomly select certain data. Okay, so let's say that we have prepared some data points and teach our neural net to learn those ones. And after that, our concern is it possible to solve get the correct result for this data point or another this data point? That is checked by our test set. So although within the training range, but it is not inside the training set. Of course, we can think about another case, the one outside the range of our current interest. So in this case, it is almost impossible to match our predict the correct data out of this relatively small training range. Okay, so anyway, so it means that well, from the viewpoint of an expert, maybe my training is not that good because test data and training data shows some differences in the calculated accuracy. So if everything is perfect, then they should be merged into similar level. So, well, I'm not saying that my data set distributed to you is perfect, but please anyway try to implement it. So it will take just a few or 10 or 20 lines to implement the overall, the core operations shown in this part. So yes, now you can do this job. Okay, so I think that's it for today's lecture. So simply speaking, what I want to ask you till the next session is implement a neural network, and please download our 2 CSV files for memorized or pre-trained weighting factors, weight, and using that one, please please calculate the accuracy of your neural network. So then yes, so you will have the ones about yes 80% or higher than 80% for your data set, because I have done it for full data set. So your training result, or if you test or if you check the accuracy for the entire training set, your data should give, your neural net should give us about 80% accuracy, and for training set you must have the numbers slightly higher than 85%. So please try to do it, and if you are interested, then maybe you may play with that neural network. For example, you can provide your own handwriting discretized in 28 by 28 cents, and check whether it really can detect your image, not the image in the MNIST data set. So, but it is just optional. So the mandatory one is please implement and calculate the accuracy for given images. So okay, that's it. So simply speaking, today's lecture just says that you have already well trained, pre-trained weightings for your neural network, and please implement a shallow neural network for MNIST detection. Okay, so that's it for today's lecture, and since we have a relatively a long time, so let me just briefly introduce what we can do with this training phase. So I would like to avoid detailed description about this training phase, but for a while just quickly think about this problem only for a while. So here, now think about this one. Well, what we do is, starting from this very large vector, make it smaller, and finally make it quite small. So let's consider this transition from layer 1 to layer 2. So in this case, there was nothing related with the nonlinear function. From this to that, we have introduced LEL function and dropout. However, in this case, the way was just L2 was given by W2 times L1. Okay. That was the operation. So this is hidden layer contents, and this is up layer contents, and there was a mapping called as weight 2, and that was it. But point is, once we generate this number, then it will give us a certain vector for given L1 vector. So for example, as I told you before, minus 0.1, minus 0.2, and 0.5, and something like that. It means that it strongly suggests that this image should be regarded as number 2, because 0.5 shows the maximum value, so it has the highest probability to have number 2. So now we say that okay, this is number 2. Then how can we recognize that is really number 2 or number 1 or 7? So usually in this supervised learning, we must label them. Okay, let's say that this is not actually number 2. Say that this is actually number 6. Then what happens to our codes? How can we measure the degree of deviation from the actual solution? For that purpose, what we do is like this. Here we have 10 entries, and if we have label 6, then this is encoded as this one, 0 0 0 0 0 and 0 0 0 6 7 8 9. Okay, here we have 10 entries, and it's a 7th entry corresponding to number 6 is encoded with 1.0, and all others are just 0. So then we say that if this neural network is perfect, then it should be able to generate this output. Any other digit have the probability of 0, and only the correct one, number 6, should have the output of 1.0. That is the one we wanted to have. However, currently we have a very long way. So what we wanted to have blah 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 1 0 0 0. However, what we have right now is minus 0.1, 0.2, and 0.5, blah blah blah. That is the one. This is our idea, and this is our reality. So what we have to do is actually our output should be, L2 output should be corrected by this amount. If our L2 output is corrected by this amount of vector, then later, even with this given L1 value, our output will be the perfect. Instead of this long L2 currently we have this L2. However, if we add this number to our L2, then it is cancelled out, and we will have the perfect one. So it means that although we have a long value here, but we understand how can we improve our output. If we add certain number, let's say that this L is the real solution or real desirable output, and this is a current output, and if we add this number into our current output, then we will have the real desirable output. Then how can we improve this situation? Because this L1 is given from our previous steps, so we say that okay, this is just given. So what we wanted to do is instead of this W2, we wanted to make a certain modification to W2 matrix. So say that although this is not the case, but let's say that if we make a certain modification to W2 matrix and fix L1 matrix, then it can give us really good, real desirable output. So we wanted to calculate the modification for W2 matrix. That is the one we wanted to do. So how can we do this job? So in order to achieve this goal, we are now doing this one. So, but for a while, actually in this course, you don't have to fully understand all of my explanation, because yes, in this semester we just introduce this stuff. So if you are interested, please revisit the next and next lectures in coming semesters. But yes, what we do is we first define so-called loss function, and there are many different ways to define this loss function. But for example, we can make the simplest one. Let me just do the simplest one. Simplest one means that here we have a difference. Then what will be the difference? The difference will be 0.1, 0.2, and minus 0.5, blah blah blah. That will be the output of our difference. Yes, and this one contains a lot of entries, but this is not easy to handle this vector quantity. So this loss function is just mapping from one output vector into a scalar. How can you do that? The simplest one is like this. Square of 0.1, square of 0.2, and square of minus 0.5, and it is summed until the 10th digit. So what we can do is so this one, what we can do in this case, let me just do it. Let's start. I runs from 0 to 9. Why from 0 to 9? This is corresponding to each entry of our error, and calculate the sum. Then it will give us this way. This is the correct solution error. The correct solution's ith component. This is either 0 or 1 minus this one, the L2 vectors ith component. Then how can you make this L2 vector? L2 vector was obtained from W2 and what? W2 and L1 vector. So, and how can we have this ith component? In order to get this ith component, actually let me do it once again. Now J runs from 0 to 99, and W2's I, J and L1J. We need this job. Okay, so this is nothing but just a way to calculate L2's ith row entry. So this is row index, and this is a column index, and here we have a column index. So we just made W2 times L1. So now we have this kind of thing. Then let me just do some calculation. Now we have defined this loss function, And what we wanted to do is just to change this w2 I comma j. Instead of this w2 I comma j, I comma j entry of w2 matrix, we wanted to introduce a small variation of that entry. Then what will happen to our loss function? If we introduce a small deviation into, so I mean that is added into our W2, then what we can expect is instead of this one, then now we have W2 comma its delta value can be added. And now due to the change of W2 matrix, our loss function can be either increased or decreased. So now we can consider this quantity. Sensitivity of our loss function with respect to W2 I comma j. We can calculate this one, and that sensitivity, as we all know, can be calculated by the partial derivative. So that's it. So let's say that I happen to be, for given I and j value, all kinds of this summation can be eliminated because we fix, for example, 3,4 component. So the part corresponding to this 3,4 component, for example, so loss function now can be written as all other terms which is not relevant to the 3,4 component plus, and now L3 minus, or L3 minus other one is W2 3 4 and something like that. We will have this loss function relevant to its certain component and all other one. So what we can do is now taking this loss function and make partial derivative with respect to its I comma j component. Please do it. Then you can find that this is nothing but, for example, if we just do this simple calculation, then you can expect that what we will get is corresponding to just something like this, 0.99. This one itself, it comes here because this is a square. Once we take the partial derivative, we will reproduce its first order quantity, and now we will have a certain partial derivative of this term. So it will give us Li comma j. So please note that what is this? This is nothing but our error, current error value, and this is corresponding to what? This is nothing but current hidden layer value. So sensitivity of our loss function for a small deviation in our W2 matrix can be obtained by the product between our error itself and current hidden function, so input layer. I mean, in this case, input layer is a hidden layer. So by multiplying these two numbers, we can generate a certain direction of update can be obtained. So please visit, if you are interested, please visit more detailed detailed and mathematically sound derivation, but point is now the direction of update can be obtained by just multiplying your error vector and hidden layer vector in certain way. So this is actually vector and this is vector, and you must generate matrix. So now this vector the multiplication is not an inner product, but instead of that we have to do other outer product. So anyway, so you can generate some direction of update. So finally, let me just come back. So by applying this kind of approach, now you can generate certain direction for updating your weighting factors, so W2 or W1 matrix. However, this is just corresponding to the direction and how much we should go. Please think about this one. Well, if you are talking about the Newton-Raphson method we have studied previously, let's say that you have to solve y equal to x0 square x minus 1, and let me just draw y and x, and it will give us this shape, and of course positive x equal to 1, this is the solution value. When we apply this Newton method, then if we are in a wrong direction, then our current Jacobian matrix gives us the right direction to improve our solution. After that, how much we proceed along that direction. That direction was also generated from this residual function and this Jacobian matrix. By taking these two components, we were able to generate the update vector for our case. However, the situation is a little bit more tricky in this case. Now, taking this calculation, the product between our current error and our input layer, now we can generate a certain direction. Direction itself can be calculated. Okay, we must reduce our current x value or solution value. Then how much? That is not explicitly available in this current approach. So what we can do is, well, maybe conservative approach is more safer than more aggressive approach. So instead of just going into that way with believing the linearity of our system, in this kind of approach, we just take very small step, and after that, oh, we are safe. Our error is relatively small than previous one, and also calculate once again the direction and go. So although that the direction of update can be obtained, but exact amount of that update cannot be obtained. So that's the reason why in this field they introduced the concept of learning rate. So it means that we should be very careful and slightly, only moderately change our current weighting matrix slightly and slightly. So that's the reason why the number of calculation needed for this optimization is much higher than number of Newton iteration we have spent for our conventional numerical analysis. Of course, in our case, our case means that your nonlinear Poisson equation or drift diffusion model, all kinds of the equations shown in the TCAD simulation are well posed, and the number of unknown and provide the equation are exactly matched. If you have 100 grid points and if you have three different unknown variables, then you are provided with 300 equations. So number of unknown and number of equations are exactly matched, and that system becomes a determined system. However, please think about this case. In this case, the thing we have to optimize, this one has the size of 10 by 100. However, the data we have at each step is just 100 and just 10. And how many data do we have? Do we have exactly 10 data points to exactly match this LW2? Actually not. We have sometimes much more data, or sometimes we have much less data. So actually this W2 cannot be, that cannot be determined uniquely. This is not well matched system. So number of unknown, so the number of free parameters and the data provided from the problem can differ quite significantly. So in this case, we cannot apply our previous technique used in the solving the partial differential equations, and we have to adopt techniques for optimization. So due to that reason, so we can generate a certain corrected direction, but the selection of that update, that is the key. So there are a lot of many different algorithms to automatically select properly the learning rate, and here I have used different learning rates for your own reference. If you are interested, what I can recommend to you and is you can implement also your own training course by using the one shown in this reference page, and you can play with different learning rates. So for example, if you reduce learning rate, then your learning will become slower but becomes more stable, and if you increase it further, then it can sometimes more rapidly approach to the how can I say, the maximum performance you can get. However, also there is some danger to become unstable. So I think that this selection of this learning rate is a matter of heuristic. So there is no given principle and golden rule to take the learning rate. So people have spent quite a long time for their own problems and learn some feelings or experience on selection of those numbers. Okay, so well, anyway, so let me just summarize our two lectures, lecture 8 and lecture 9. Although I have a long plan to implement some stuff, neural network stuff, into this course eventually, but it's not for this very beginning. So in this year we will just stop here, and what we have done is just to implement a simple neural network for detecting MNIST1. So you have not done the training by yourself. I just gave you the pre-training one. So if you feel that, oh, I wanted to do it by yourself, then it's not that difficult. Actually, when you visit the reference page, then you can find a few lines to eventually update your um, weighting factors, weighting metrics. So I strongly recommend you to do it by yourself, and please let me know what happens if you do it by yourself. Okay, so do you have any question? So if you don't have any question, then I would like to wrap up today's lecture, and we will come back to our original or usual lecture content from lecture 10. Okay, thank you for your attention.